Now that we talk about, so we only have one more boundary condition to think about, and that's on that wing. And I mentioned this thing of no slip boundary condition. So the fluid here comes here. The velocity of the fluid at the wing contact is 0. So you normally think of about a flow profile that would look something like this. The velocity file would look something like this. It's 0 right there. Okay? So how do we impose this here? Well, you're not trying to impose this on the wing. You're trying to impose that the fluid itself, U and W, should be 0 on the wing. So it might be enough just for us just to say, look, if I want U and W on the wing, then psi of Z, psi of X should be 0. So I could think about taking basically whatever the norm of this thing is, and I could just say, well, look, if I look at the gradient across the boundary, right? The gradient is the derivative of this thing, and and the derivative is going to have components, this and this. If I just set everything to 0 there, everybody's going to be 0, and that's going to imply U and W are 0.
Setting the gradient to 0 or
setting the boundary flux term to 0. So so how should you say it? So it's n dot times gradient of the field across on this boundary. I want to do that. So if I take a dot product for any angle, this thing here has these components to really make this hold for everywhere. It's like, this is going to imply that these guys are going to be 0 for all angles, which will give you.
plus or minus 1, and they were both plus 1, and the normal would not cancel out.
You potentially could, but for generic geometries, that's not going to be the case. So then you just say, I can just impose that on that wing, and I have something like the no-slip boundaries. Okay? Yes?
W there is velocity in that Z direction.
That's right. That's right. So this is the U component. So yeah, if we think about velocity, here's the U component and the W component. Okay? So we're just going to kind of program this up, see what it looks like, draw some arrows. And by the way, when we plot this thing, we're going to get the solution stream function, psi. I don't want the stream function. I want its derivative. Now, it turns out you can actually impose, you could say, well, what I want to do is calculate this and this. So pretty close to this is the gradient of psi, right, which is more like this. There's no minus sign, but let's just roll with it for now. I have a sign off, but let's just roll. Right? I can tell this thing to do what I want, but I'm not exactly sure how to tell it to do what I want. So we'll just pretend that I know what I'm doing and go. And if nobody calls me out, it's last day of class. I'm just asking for a little gift here. All right. So everybody good? So we're going to try to program something like this up, just show you kind of what it looks like, show you how you might design this, and go from there. And then we'll play with my iPad slightly, a little bit. I don't know. We can't. Unfortunately, I can't project the thing I really want on the iPad, but we'll dim the lights, and I will give you a little movie, okay? All right. So everybody good with that? Questions so far? No, or are we all good? We're all good. Okay, so let me see. Perfect. Okay, there we go. All right. P tool. Nice. Oh, okay, there we go. Everybody good with that? Good? All right, so it's kind of like last time. Now, remember our buttons. Everything's a button-driven thing here. Everything is just you start from left, work your way to right, and you get yourself your solution. Okay. So let's go ahead and start putting our boxes in. Let's just draw a little domain. Here's where our fluid is going to flow, right in there. Region 1. And let's start off with a basic wing. And we'll make it an ellipse. Sort of looks like a wing, right? Of course, I don't think you can fly with an ellipse. Can you fly with an ellipse? I think if you go fast enough, you can fly anything, by the way, including a cylinder. If you have a big enough rocket, yeah, I think you can fly anything. Always. One of my buddies said when we were back in high school, we were skiing, and it's one of those things like, oh, let's see that little bump there, and Because you get enough speed, you can catch air off anything. And he totally was right. Just that you land harder. All right, so like that's being a cylinder. All right, so there we go. I have region 1, I have an ellipse, and what I want to do is I put the minus sign for the domain. So my domain should be this, the bigger region. Subtract out this region, so that's going to create the hole where I don't want any fluid flow. Okay? Now, that's moving left to right. That's going to happen. Now I just go to push the boundary button. Okay, there are my boundaries. Nice. Now, it's really interesting. I want to point something out here. You see this ellipse? You see the arrows? We talked about the meaning of the arrows, and I don't really know the meaning of the arrows, but I do know that this ellipse got broken up into 4 parts. So for instance, right here, if I double-click that, boundary conditions on that. And you see I could specify on one segment. So I'm going to go put Neumann on here. So here's what we're talking about. The normal with the gradient. So this is like the derivative terms. And Q and G are naturally set to 0 to begin with, and that's exactly what I want here. So we just want the gradient to be 0. So it's kind of like approximating, like, hey, no slip boundaries. Fluid velocity is 0. So the stream function, the derivatives of the stream function will be 0, which is equivalent to saying that the fluid itself will be 0 there. Okay, but notice it colored this section blue. Now, I don't exactly know why it does this, but when you do ellipses, it breaks it up into pieces. And why would you want to break up your ellipse into a bunch of pieces? But here we go. Let's just do Neumann for all of them. And in fact, pretty much, we have to impose Neumann on everything. Why? Because we're really imposing boundary conditions on the velocity of the field, not on the stream function. So anytime we go to a boundary, we actually have to say, well, if I want to get to the velocity field, I actually have to get to the derivative to impose it, right? So on every single piece of this boundary, we're going to have to pose some kind of derivative condition.